Welcome, future data science legends. This course is about learning how to tame uncertainty. Statistics is our way of transforming messy data into meaningful information, the kind that helps us make decisions even when the future is fuzzy. Think of descriptive statistics as an aerial view of the jungle of data. You don't see every leaf or insect, but you get the big picture. Where the rivers flow, where the mountains rise, where the mango trees are, and where the hungry tigers are probably hiding. Now picture a world without statistics. No modern medicine. We couldn't test whether treatments actually work. No psychology theories, because you'd never know if that experiment with volunteers was real science or delusions of a crazy cult. Farmers wouldn't know the best conditions for crops. We'd still be guessing how much irrigation is best and try to reach it through rain dances. Even physics would grind to a halt. Quantum mechanics relies on probability, because the universe at the smallest scale really does roll dice. And worst of all, Netflix would recommend random shows that have nothing to do with your watch history. Today's presentation is about setting up that aerial view. What statistics is, where data come from, and how we start making sense of it before we dive deeper into the jungle. Here we have statistics as a full process: collect, organize, analyze, interpret. Most administrative decisions need this process. Colleges don't expand resources based on gut feelings. They look at actual student usage. Without data, administrators would be like, well, I saw 3 students in the library last night, so clearly we need a 24/7 Starbucks in there. Not exactly evidence-based policy. A population is the whole group we want to study. A sample is the smaller representative group we actually measure. A parameter is a number describing the population, like the true proportion of Canadians who support a new policy. A statistic is the number we get from our sample, like the proportion of supporters in the 2,000 people we actually surveyed. Here's another example. The true average saltiness of the entire oceans on Earth is a parameter. We can't possibly ever know the exact value of this parameter. A statistic is the number we get from our sample, like the average saltiness from 100 jars of water collected from different spots. If you use correct sampling techniques, your statistic would be a good estimation for the parameter. However, if those jars mostly come from river deltas, your statistic will underestimate the saltiness of the whole ocean. That's the danger of a biased sample. You don't just miss the big picture, you get a completely distorted one. Suppose we want to estimate the true average weekly study time for all Dawson students. The entire Dawson student body is our population. But surveying every single student would be too expensive, too slow, and half the students wouldn't even answer because they're too busy studying, hopefully. So instead, we take a sample, say 200 randomly chosen students. The true but unknown average for the whole population is the parameter. The average study time we calculate from our 200 students is the statistic. If our sample is representative, that statistic will be close to the true parameter. But if we sample only night owls hanging out in the library at midnight, we'll probably overestimate how much everyone studies. That's the danger of bias in sampling. Variables are just characteristics we measure. First split, qualitative versus quantitative. Qualitative variables describe categories, like program of study, eye color, or favorite pizza topping. No math involved. You can't average pepperoni and mushroom. Quantitative variables are numbers. They can be measured and compared mathematically. But even here we have two flavors. Discrete variables are countable things, like the number of courses you're taking or the number of coffees you need to survive Monday. Continuous variables can take any value along a scale, like your height, your weight, or the exact time it takes until it's your turn at Tim Hortons when you're already late for class. Continuous and feels infinite. So in short, categories versus numeric, and if it's numbers, see whether you are counting with fingers or measuring using a ruler, a scale, or some other more sophisticated device. Remember, ratio scales have a true zero. That means zero really means none of it exists. Interval scales don't have a true zero. For example, 0 degrees Celsius doesn't mean no warmth exists. Another difference is that with interval scales, ratios do not make sense. For example, 20 degrees Celsius isn't twice as hot as 10 degrees Celsius, it's just 10 degrees warmer. If 0 means nothing is there, it's ratio. Examples of ratio scales include height, weight, money. And yes, my bank account after paying bills and mortgage is the perfect real-life demonstration of a true zero. IQ is measured on an interval scale. Differences are meaningful, but there's no true zero. So an IQ of 0 doesn't mean no intelligence. It doesn't mean the brain is empty of thoughts. An IQ of 0 means unusually dumb and astronomically unlucky, because even by random guessing, probability says one would eventually stumble into a right answer. If 0 IQ really meant no thought at all, half of YouTube comments would not exist. Only experiments, with proper design, can support real causal conclusions. Observational studies can show associations, but correlation isn't causation. Otherwise, we'd have to believe that Nicolas Cage releasing a movie makes shark attacks go up, or that simply keeping an umbrella in your car increases the odds of a traffic accident. These bizarre pairings remind us, without controlled experiments, we're just pattern spotting. And humans are really good at spotting patterns, even when the universe is clearly just messing with us. Picking the right sampling method is crucial. It's the difference between getting a representative snapshot of the population or ending up with a biased mess. Good sampling gives you results you can actually trust. Bad sampling, well, that's how you end up with headlines like "Study shows pineapple on pizza is the most popular topping," and then we all suffer. The bottom line: choose carefully or risk making claims that no sane statistician or Italian would ever endorse. Choosing a sampling method isn't random luck. It depends on a few key factors. 1. Population structure. If the population has clear subgroups, like programs of study, stratified sampling makes sense. If it's more uniform, simple random might do. 2. Resources and time. Some methods are cheaper and faster. Cluster sampling saves effort when people are naturally grouped, while SRS may be ideal but costly. 3. Accuracy needed. Stratified sampling often gives more precise results than simple random if groups differ a lot. 4. Practical access. Sometimes you can get a complete list of the population, so you opt for systematic. 5. Bias risk. Convenient sampling is tempting but usually a bad idea, unless you want your results to reflect only whoever was in the cafeteria. In short, your choice balances realism, time, and budget with reliability, minimizing bias. Bad sampling means your results are either always wrong or they vary wildly from sample to sample. So before starting data collection, work on your sampling strategy. Guidelines to keep in mind: 1. Sample size. Too small equals noisy results. Aim for a large enough sample to reduce variability. 2. Representation. Make sure your sample reflects the population's diversity. Avoid leaving groups out. 3. Randomness. Every individual should have a fair chance to be selected. Randomness keeps bias away. 4. Practicality. Balance ideal design with available resources, time, budget, access. 5. Non-response and bias control. Plan ahead for people not answering or giving misleading answers. So one can say, a good sampling design is like choosing Avengers for a mission. You need enough of them, from different backgrounds. You need the right mission strategy that balances idealism and practicality, and finally you need a plan B. If we skip controlling for gender, we risk a classic confounding disaster. Say more men land in the treatment group and men recover faster naturally. Suddenly it looks like the drug is a miracle. Or if more women end up there and recover slower, we might say the drug doesn't work. Moral of the story: without control, you're not testing the drug, you're just mixing effects and wasting everybody's time. If we neglect randomization, we open the door to hidden biases. Imagine all the healthier patients ending up in the treatment group and the sicker ones in the control group. Now the miracle drug looks amazing, but really it was just group imbalance. Flip it the other way, and the drug looks useless because it was only given to the toughest cases. Without randomization, your experiment becomes less science and more rigged talent show. If we neglect replication, we might base our conclusion on just a handful of lucky or unlucky patients. Maybe 3 people took the drug and they all got better. Great, but that could be pure coincidence. Or 3 took it and none improved. Same problem, just unlucky this time. Replication makes results believable. One observation might be a fluke. Many observations show a pattern. Without replication, our results are as shaky as flipping a coin and declaring heads cures all diseases. If we neglect blinding, expectations can creep in and mess with results. Patients who know they're on the real drug might feel better just because they believe it works. Classic placebo effect. Meanwhile, doctors who know who's in which group might unintentionally treat patients differently, giving the drug group a boost or the control group less care. Without blinding, you risk measuring psychology instead of pharmacology. Your new wonder drug turns out to be nothing more than confidence in pill form. Choose the display that answers your question with least ink and most clarity. A good chart is worth 1,000 words, and a bad one is worth 1,000 misunderstandings. Same data, 2 views. Bars make it easy to compare categories, library versus home. Pie shows share of the whole, but precise comparisons are harder. Pie charts are like dessert. Fine occasionally. Don't make a meal of them. Bars sorted by frequency. Line shows cumulative impact. Here, late plus format already covers 68% of errors. Fix those first. This chart is named after Vilfredo Pareto, an Italian economist and sociologist. The Pareto principle, also called the 80-20 rule, says, in many situations, a small part of the causes produces most of the results. For example, in business, 20% of customers often bring in 80% of the revenue. In studying, 20% of the chapters may contain 80% of the material that will be on the exam. In work, 20% of tasks may give you 80% of the productivity. And 20% of your friends at a party eat 80% of the chips. And somehow they're always the ones who forgot to bring anything. Clear upward pattern. More study, higher scores. One outlier, low hours, high score, suggests prior knowledge, lucky guessing, or successful cheating. Use a scatter plot before computing the correlation coefficient or fitting a regression line. Most scores cluster around 65 to 95 with a small skewness to the left. Histograms reveal distribution shape, skewness, and multimodality better than raw tables. Dot plot shows clustering, several in the low/mid-20s. Stem and leaf preserves exact values, handy for reading medians and spotting outliers in small samples. Median is 32. The middle 50% are between 25 and 40. Whiskers are at 18 and 52. To compare groups, quickly use side-by-side boxes. Let's break down these ethical checkpoints. Transparency. Always share your methods and limitations. If you only surveyed 50 students at lunchtime, say so. Otherwise, people might think it applies to all 10,000 students. Transparency keeps your audience from assuming too much. Privacy. Guard personal data like it's your Netflix password. Even if names are removed, sloppy handling can still allow people to be re-identified. That's a quick way to lose trust and maybe your job. Avoid misleading visuals. Cherry-picking data or stretching axes can make results look dramatic or completely meaningless. A bar chart starting at 95% instead of 0% can make tiny differences look like the Grand Canyon. Example: a responsible survey report should list the sampling frame, response rate, wording of questions, plus any uncertainty or possible bias. Without that context, your data is like a headline without the article, misleading at best. Ethics in data isn't about being boring, it's about being credible. With great datasets comes great responsibility, and even greater footnotes. Reinforce mapping from variable type to display by paying attention to these details whenever you see a chart from now on. This becomes automatic with practice. For now, if you answered pie chart for everything, we need to have a slice of intervention. Let's imagine a real college life research question. Does the amount of sleep students affect their GPA? Variable types. Hours of sleep is quantitative and continuous. GPA is quantitative, but usually treated as interval. You might also include categorical variables like major or year of study. Observational versus experimental. You could do an observational study by surveying students about their sleep and GPA. Or, if you were ambitious and had no ethics board, you could run an experiment by randomly assigning some students to less sleep, though good luck getting volunteers. Sampling strategy. Instead of just asking your friends, convenient sample equals bias, you'd want a stratified sample across programs and years. That way, engineering students pulling all-nighters don't dominate the results. Displays. A scatter plot could reveal correlation between sleep and GPA. A histogram might show the distribution of sleep hours. A box plot could compare GPA across groups, e.g., less than 5 hours, 5 to 7 hours, 8+ hours. This example ties everything together: variable types, design choices, sampling, and visualization, just from one everyday college question. These fundamentals power everything else we'll do: description, probability, and inference. It's like learning kitchen basics, knife skills before soufflé, unless you enjoy chaos and confusion. Uncertainty is the invisible boss of all sciences. Physics, biology, psychology, they all deal with messy data, measurement error, and incomplete knowledge. Statistics is the language we use to tame this chaos. That's why it's probably the most applied branch of math. It gives us tools to measure uncertainty and make decisions anyway. Without it, scientists would just be shrugging in lab coats.